to Einstein's mechanics. Today we are going to start with fluid mechanics, an aspect of mechanics which is very interesting called the fluid mechanics. And kindly subscribe to the channel, like and share the video, and you'll benefit from these tutorials. For objectives of the day, by the end of this chapter or this lecture, you should be able to describe fluid mechanics. As an average person, anytime they mention the word fluid mechanics, there is some level of idea you have to have when this fluid mechanics is mentioned because it comes with its own understanding. And trust me, you are going to find everything and understand everything about fluid mechanics. We will also discuss the fluid properties, which will help you to distinguish between various fluids, which will help you to choose a particular fluid, and this will also help you to understand the behavior of a particular fluid. That's interesting. We will also discuss the dimensions and units. We are much interested in dimensions and units when it comes to anything mechanics, and fluid mechanics is not an exemption. Trust me, you will enjoy this lecture and everything about fluid mechanics. Fluid mechanics. The first question an average person will ask is why fluid mechanics? Why this course? Fluid mechanics is highly relevant in our daily life, very important. We live in a world full of fluids. Everywhere is word fluid. We will see why we are saying we live in a world full of fluids. Someone may ask, thinking fluids are only water, and by the end of the lecture, you will understand why we are saying the world is full of fluids, how come, and how does this happen. It does not only explain scientific phenomena, but also leads to industrial application. Fluid mechanics is practical in our daily life, in the industry, everywhere we find ourselves, we use the idea, the concept of fluid mechanics. Let's consider some examples where fluid mechanics plays a role by way of ensuring that homes get access to electrical power. So we are talking about electricity here. One, electricity. Engineers have to develop technologies that include water turbines. Wow. As we move forward in this lecture or in fluid mechanics, we will encounter these water turbines, the wind turbine, the electric generator, the motor, and the electric grid systems. And we know that as these turbines are turning, they are connected to generators which generate what? Electricity. And by the idea of fluid mechanics, we have converted the power, the hydropower from water to produce electricity. This is quite interesting, and that's the power of fluid mechanics. And most of our farming activities demand that we keep supplying water to them that keep them alive. Are we good? Our plantations, they need water. So how do we get this water from one particular point to where our irrigations are? Assuming this is the source of water, and here is our plantations. So, for instance, engineers design the irrigation system to supply to our vegetables and other plants of interest. So here, by the understanding of fluid mechanics, I can design an intermediate channel between these 2 points by virtue of a pump, which will now transfer the water source to the plantation. It would have been difficult moving water from one source to where our plantations are. But with the idea of fluid mechanics, engineers are able to develop a system which will help us. These are some of the applications in the industry where we live around us that we apply fluid mechanics. Trust me, we will learn a lot, and fluid mechanics is practical. What is fluid mechanics? So, what then is fluid mechanics? It is the science. Fluid mechanics is a mechanics, so it is a science that deals with the action of forces on fluid, either at rest, that's static fluid or fluid statics, or in motion, what we call fluid dynamics. So fluid mechanics is very simple. Is we studying the action of forces on fluids either at rest, that's what we call fluid statics, or in motion, what we call fluid dynamics. The effect of forces on these fluids, that's fluid mechanics. And we have categorized this fluid mechanics into two. We have what we call the hydrodynamics. When we talk about hydro, it should give you a clue, and we will get to know why hydrodynamics. We also have what we call the gas dynamics. So as we are studying the effect of forces on these fluids, it can be a hydrodynamics, it can be a gas dynamics. What is a hydrodynamics? When we talk about hydrodynamics under fluid mechanics, here it deals with the flow of fluids, the flow of fluids for which there is virtually no density change. So with hydrodynamic study, we assume no density change. Are we good? No density change, meaning the flow is constant with constant what? Density. Examples include flow of liquids and flow of gases at low speed. We'll get to understand more as we dive into the fluid mechanics, go to calculation parts, and we will understand why there is no density change. So any study on any fluid in motion that has no density change, we classify them under the hydrodynamics. What about gas dynamics? The gas dynamics deals with fluid that undergoes significant density changes, very small density changes. So with this example, as we study the fluid or as the fluid is in motion, its density changes from one particular point to the other. Let's assume this is a continuous system. This is a continuous system, let's say a nozzle. Thus, it's reducing. As this fluid is moving from this particular point going, the density at point 1 differs significantly from point 2, and fluids behaving in such way are classified as gas dynamics. Examples are high speed flow of a gas through a nozzle and the movement of a body through the low density air of the upper atmosphere. So, for example, it mostly happens when gases flow through a nozzle, and with that we will see a significant density change. So these are the difference between hydrodynamics and gas dynamics. That's interesting. What is a fluid? We have to also understand what a fluid is. Now we know what fluid mechanics is, studying of what fluids under the effect of forces, whether in motion or stationary. What then is a fluid? What are we calling fluid? Averagely, when you ask a person what is a fluid, the person is most likely to say it's water. And we'll see if this is 100% correct. Yes, water is a fluid, but what else? When we say fluids are water, then we've limited the scope of fluid. What then is a fluid? A fluid is defined as a substance, any substance, that will continuously deform, that is, flow under the action of shear stress, no matter how small that stress may be. Are we good? So any substance that continuously deform under the action of a shear stress. no matter how small the stress. That can be classified as a fluid. So for example, if we are considering water, let's say I have water poured in between this point 1 and 2, or a stagnant water over there. And assuming that there is a push from this system tries to push this water. That means an action is being done here. An action is being done. And now we know that it will start to flow. And as it starts to flow, then it is continuously what? Deforming. Because the shape, as at this point, would differ continuously as times what goes on, because there has been what? A force applied here. And that force causing the motion is what we call shear stress. In strength of material, we saw that shear stress occurs when bodies slide over each other. Let's assume these two, body A and body B. If a force is applied here, P, and a force is applied here, P, there will be a shear at the meeting point. This A will slide over point B, causing a shear stress. The same thing happens to the particles of the water. They will try to slide over the surfaces of each one, and that's causing what? A shear stress. Are we good? So fluid, in simple terms, any substance that will deform when a force is applied to it to cause a shear stress, no matter how small. Because if I pour any small amount of water over there, it will start to what? Move in the direction the force or the shear stress is causing it to move, no matter how small the shear is. That is a fluid. Are we good? We said the rate of deformation as the flow is happening. There is a deformation. Deformation, from our simple understanding, when a body changes what? Shape or size, there's a deformation. So initially, the fluid had its shape, but with time, as the shear stress causes motion, the shape is going to what? Change, meaning there is going to be a deformation within the water. And that's what we called what? The rate of deformation. That's the strain. So this is saying that the strain or the rate of deformation of a fluid is related to the applied shear stress by a property called viscosity. We cannot exempt viscosity as we are studying fluid mechanics. So this line is telling us that anytime there's a deformation, a shear stress is causing a movement inside a fluid, being it a gas or a liquid, that deformation change in shape is related to a property called viscosity. We'll talk much about viscosity in our next or upcoming slides, and we will understand why this line is saying so. As I said earlier, a fluid can either be a gas or a liquid, so we should not limit the idea of fluid to only water. Gases are also fluids. The difference in behavior of solid, liquid, and gases are due to the differences in their molecular structure. For this, we know that the difference between solid, liquid, and gases is due to the arrangement of their molecules. Are we good? So this is a solid, and with liquid, they are quite separated. This is liquid, and for a gas, the molecules are widely spread for a gas. So the difference between solid, liquid, and gas is just the differences in their molecular structures. Are we good? So we look at some differences between solids, liquid, and gas. Very simple. So based on their macroscopic description, the arrangement of their molecules, how these molecules behave, we can get some differences as I drew the diagram in the previous slide. Solids hold their shape, no need for a container, meaning they have fixed shape. The shape of solids are fixed, but liquids take the shape of the container and will stay in open container. So they take the shape, instead of them having fixed shape, they change shape as the container is being changed. Gases expand to fill a closed container. As gases are placed inside a closed container, remember, if it is not closed, they will leave because they try to what? Separate from each other. So when the container is a closed system, then they expand to fill the whole container. So based on the arrangement of their particles, these are the differences between solid, liquids, and gases. Let's base on their density. Remember, we talked about a significant change in density when we were talking about the gas dynamics or gas hydrodynamics. So based on the density, solids have high density, very high density. Density is the mass to volume ratio. The mass to the volume ratio, meaning if I place a block over there, the mass of the block, let's say 10 kg to the volume here is 2 meters, 1 meter or 3 meters. Then the ratio of the mass to the volume, let's say this is a three-dimensional block, and let's say this width is 1, so the volume will be 2 by the 3 by the 1. The mass to volume ratio of this block is very high for solids. Let's look at liquids. It has moderate density. It's not as higher as solids, but not as lower as gases. So it's moderate. And gases have lower density, very low density, because looking at the mass to the volume, it may occupy a very large volume. Let's assume this is a container, very large container, let's say about 20 meter cube, and just 1 kilogram of a gas can expand to fill the whole container. So if we are to find the density, it will be a 1 kilogram mass to a 20 meter cube volume, which is very large or very small, which is very small to give us a low density of the gas. If we base on the effect of stress, that's the shear, we are talking about the shear stress here. How does shear stress? Remember, we were saying the shear stress causes the movement of what? The water molecules within a system. If the shear stress is applied, they will begin to slide over each other and motion begins to what? Okay. So how are solids, liquids, and gases affected by shear stress? Please pay attention. Within the fluid mechanics, our motion is going to be based mostly on this shear stress. Solids produce deformation. When shear stress is applied, or the effect of shear stress on solids is that it produces deformation. So if this container begins to shear on the surface, there will be deformation. It is going to deform from its original shape. It's either this will cut off completely from its base to cause a deformation. That's for solids. What about liquid? It produces flow. Instead of the shear to cause deformation, as the deformation is caused, there will be a flow. Let's assume that the particles now begin to move in certain motion. So this one will begin to slide over this particle, begin to slide, and as it is sliding, it is also going to move. So the effect of shear stress on liquids is it produces flow. The same thing happens to gases. Remember, we were talking about fluids, which is liquids and gases. We can also base our differences based on their effect of normal stress. Now we've seen how shear stress affects liquid, solid, and gases. What about normal stress? From basic mechanics, we now know what a normal stress is. We now also know what a shear stress is. If we don't know, we have to go back to the basic mechanics tutorial and find out. So based on the effect of normal stress, solids, liquids, and gas produce deformation that may lead to volume change. So when normal stress is acting upon solid, liquid, and gases, it produces deformation. Very simple. They are deformed. No motion is caused in the liquid and the gas again. It's only the shear that causes the motion. But for normal stress, there is deformation. And we see that anytime there's a deformation, it is also going to lead to volume and shape what? Change. Based on their viscosity, viscosity is still anonymous here. We'll talk about it so much. So based on their viscosity, solids do not experience viscosity, and we will know why. What is viscosity? So if we are going to differentiate between solid, liquid, and gases, solids have no experience with viscosity. Liquids have high viscosity. Thus, viscosity decreases as temperature increases in liquids. So for a liquid, as we increase or as we decrease temperature, then the viscosity also what increases. Are we good? All right. What about gases? Gases have low viscosity, and their viscosity increases as temperature decreases in gases. The last thing we will base to classify or differentiate between solid, liquid, and gas is their compressibility. In fluid mechanics, compressibility is also very important, and we will also talk about it. Solids are difficult to compress. For example, if I'm talking about compressibility, this is a solid, and if I'm trying to compress this solid, imagine this is a rock. How easy am I going to compress it? So it is difficult to compress. And if liquid, let's say a liquid is also in a container and I want to compress it this way, it is also difficult to compress, because when we look at the molecular movement or structure, the solids are closed. And if I'm to compress, which space are they to move? So they are closed, which makes compressibility very difficult. The same thing happens to the liquids. But we can see that compressibility in solids will be much higher as compared to what the liquids, because of the arrangement of the particles. And gases are easy to compress because look at their molecular arrangement. So I can squeeze this to come and meet that, which is very easy to compress. I hope you enjoyed this episode 1, and this is just introduction. Trust me, you will love the course. Find out the episode 2 and the other episode. Share the video to your friends, comment, like, and follow for more. Thank you.